Thank you for joining the Once Changing the World, India's first future tech meets sustainability podcast. And today I'm delighted and honored to have Mr. Aran Nayebi, who is an assistant professor at Carnegie Mellon University's Machine Learning Department, a co-faculty member at the Neuroscience Institute, and holds a courtesy appointment Robotics Institute lab. The NeuroAgents lab works at the intersection of neuroscience and AI, reverse engineer animal intelligence, and build the next generation of autonomous agents. Previously, he was an ICoN Postdoctoral Fellow at MIT. He completed his PhD in the Stanford Neurosciences Program, was co-advised by Yamins and Surya. He's got a master's in computer science and majors in mathematics with a secondary degree in Symbolic Systems at Stanford University. The topic of discussion is reverse engineering animal intelligence to build next generation of autonomous agents. So Aran, really appreciate you taking time and being part of the podcast. Wanted to start with large language models. What do you think is like the problems with large language models? Do you think scaling might lead to these intelligent machines or artificial general intelligence that you're talking about? Or do you need a complete alternate approach, which people such as yourself are going towards, like the NeuroAI approach?
Yeah, it's great to be here. And that's an excellent question and one I think about a lot. I would say that, in principle, scaling can certainly lead to intelligent behavior. Already by the universal approximation theorem, if you have an infinitely wide MLP, with enough data, you can fit any function. And so if intelligence is a function, then in principle, it can be fit. But, in practice, though, the situation is very different, right? So we often deal with finite amounts of data and much smaller sample sizes needed in order for this universal approximation theorem to guarantee anything useful. And so that's where inductive biases play such a strong role, right? So, in practice, even with internet scale data, a two-layer MLP, which is what the universal approximation theorem is giving us as a good architecture, isn't used. It's not great, right? And so we need to be clever and come up with good inductive biases like CNNs or like transformers, as we're seeing here in language, at least. Already people, who are, for example, working on test time reasoning, for example, can draw out curves of how much data you might need to continue to improve LLMs. And so the critical thing is that the amount of data needed would astronomically be more than the resources we could all put together for it to be viable as the only solution. So while in principle, absolutely scaling is a possible way to intelligence, it's not on its own a practical way to intelligence, at least the kinds of general intelligence that we're trying to replicate that, say, the brain does, for example. And I think that there's two things that are needed, right? I'll first start with the kind of smaller order thing, which is that, maybe for language or language-like tasks where the tokens are discrete and each token has a very semantically meaningful attribute to it, right? Language, we have words, right? And they're naturally very easily tied to each other just by construction. That I think maybe something like the transformer as inductive bias is a reasonably good one. Attention in particular, right? Multi-layer and multi-headed attention. When it comes to, I think in other domains, like in vision, for example, or embodiment, so like in robotics, that the notion of token actually starts to matter here, and it's very different and it's harder. So right now, right, a very common way to tokenize these models in those other domains is random patches of images, right? And it's not semantically as meaningful as words are, in language. And there, the scaling laws haven't been actually even as favorable as, nowhere near as favorable as in language. We've gotten some progress, but ultimately, both in doing the tasks and also learning representations with vision transformers in terms of even better matching the brain over, say, standard CNNs, hasn't really led to any improvements either on the intelligence side or the matching the brain side either. And I think part of this fundamentally comes down to needing new architectures and new tokenization strategies, at least, if that's what we want to call it. But really new architectures in these other domains of vision and embodiment that scale better, right? So like companies like Tesla, you can collect tons of data. Actually, they have like 100-year, literally a century worth of video data from their cars going around the world. So like data is not the limitation here. It's that the current architectures are just not scale. They could in principle, right? Like if you, again, an MLP is all you need, but a 2-layer MLP. But in practice, even these architectures, these transformers don't appear to be sufficient to scale practically. And that's the key, is practical scaling. So there's that one domain. So like, okay, there's this like, pre-training with the right architecture, I think still needs some improvements when it comes to vision and robotics. So that's one. And I think that's important. It's going to be fundamental. And I think that's like a more short-term thing. Item number 2 is kind of like in the long term, right? Where I do think there is a sort of paradigm shift that needs to happen here, which is that we need to go beyond pre-training, right? So I sort of think of it as, it kind of going back. I always kind of ground things back in the brain and how the brain was evolved, for example. I started thinking of pre-training. People complain that, these models use a lot of data to be pre-trained on. But actually it's compared to humans, right? But actually the thing that is kind of discounted from that argument is that humans were evolved, right? And all animals were evolved for, billions of years. And that's something we kind of like scoop under the rug, and it's in our genome, right? And then we develop and like learn how to interact with the world like quite flawlessly on average. And so I sort of think of this like large scale pre-training as really just doing a faster version of evolution. Backprop is a great way at finding solutions. And I think that's the first step to building an intelligent system. So in other words, again, in practice, that pre-training is all you need, but in principle, but in practice, it's not. And not only doesn't appear to be the case in vision and embodiment, but I think we need to go beyond pre-training too, right? At the end of the day, as you interact with the world, you're going to constantly encounter out of distribution things that weren't in your pre-training data. And just kind of continuing to add it to the pre-training data kind of defeats the point of intelligence, which is to like take what you've gotten to at this point in your genome, in your pre-training, and then extrapolate beyond it. And I think the deeper lesson here is that really, and one thing that we're getting from neuroscience too, from decades of it, is that the brain is largely a modularized system. So in other words, there are subsystems that interact with one another and update both each other, but themselves over time through interaction, through development. And that I think is the kind of one of the most critical missing pieces right now for building ultimately autonomous agents. Is the pre-training is great. I think large-scale pre-training is maybe the way to get those individual modules, but we still need to figure out, not only do we need to figure out the architectures and loss functions better for vision and for the vision modules, for example, and maybe the motor modules, but even if we got there, like I think there's still this other stage of like, now you got to make the modules interact in interesting ways. And so that gives rise to figuring out a general purpose cognitive architecture for agents. And that's what we're trying to figure out here by like going back to the brain where we have a blueprint of then trying to do this reverse engineering strategy, which is, what are the principles of an agent architecture that are both conserved across species and also, what are differences across species that give rise to differential abilities. And so that's kind of grounded in this larger science of intelligence that, you're building machines, but you're also comparing against a brain to better understand this general purpose architectures as we go forward to build lifelong learning agents.
Right. Interesting. So, Aran, tell me, when you're talking about these reverse engineering animal intelligence to build, these next gen autonomous agents, how do you go about it? What's the approach? What are the animals that you're kind of modeling? Because at this point in time, we've done these human connectomics project. We've got these brain organoids. There's this Google and Harvard, which has mapped a cubic millimeter of the human brain. Currently, I think, in the connectomic space, we only have mapped a fruit fly. So when you're talking about reverse engineering an animal, is there a specific animal that you're looking at, and what's the process?
Yeah, that's an excellent question. So right now, we're primarily looking at animals that we can get whole brain data from. And, with the rise of like improved neurotechnology, the number and type of animals is changing that we can do this with. So for now, like we're focused on, like in the very short term right now, it's like Drosophila, so like fly, like you mentioned, that has its connectome, and also zebrafish. So these are fish that when they're larvae, you actually, their brain, their skull is actually transparent. So you can actually see through their brain and image it while it's moving about. But, you know, in a lot of my own past work, actually, I've worked with both mouse data, monkey data, and even human data. So the idea was, you know, a lot of my work in my PhD was to basically first try to understand, is there a kind of like reverse engineering language? So if I give you brain data, can we try to infer what's going on with that brain data at a high, you know, in terms of like functionally, like what's going on? What are the like algorithms that are kind of most consistent with that brain data? And, you know, to give an analogy, I guess, to like, if you imagine if you were trying to reverse engineer a computer, right? So you could imagine recording from while the computer runs a program from the transistors and recording the voltages, and you collect all this data. And this is effectively what neuroscience does, right? It sticks electrodes in those electrical components of the brain and gets back these voltages. And the critical piece is that you can't just stare at that data and infer in a lot of settings what is going on. Only in special cases can you do this when they're simple enough, sure, but not in general. And the way around this is actually to take the computer, take the brain that you have the data from, and build another computer next to it, and run that program and just see, is there any similarity between those transistor outputs or those chip outputs to the ground truth system that you're actually comparing against. And in neuroscience, computational neuroscience is building a model. So building, in this case, an artificial neural network, and it's parameterized by a task, and which is like a loss function and data set, and an architecture, and then a learning rule that we optimize. That's the simulation of the evolution, like a proxy for evolution, basically. And then we ask, do those internal components actually match the brain? And just, you know, the one thing that's kind of empirically emerged is that actually you can learn a lot about the brain, not just in interesting animals like humans or primates, but it can cut across the species barrier too, like in rodents as well. So showing, you know, a lot of, you know, my own work and those of others shows that there's this kind of general task optimization strategy that if you optimize the neural network for the right tasks with the right inductive biases, you can actually recover with reasonable accuracy the internals of the system matching the brain too, across species and across brain areas.
Right. I mean, you know, our brains, I mean, it's extremely complicated. 8 billion neurons, 100 trillion synapses, the way they fire and wire, it brings about all of 5 senses, sight, sound, touch, smell, and taste. I mean, how does that differ from an animal? And you know, with the brain data, it's very, very noisy and very messy. You know, machine learnings, they prefer like clean data. What are these technical challenges, and how do you kind of overcome these technical challenges of this? Right. Yeah. So
absolutely. So that's a great question. So that basically comes down to really ultimately defining a metric of comparison. So, you know, a metric of like what counts the models as good matches to the brain. And so this kind of comes in 2 stages. The first stage is that, yes, absolutely. So neurons have inherent variability. You know, for example, you know, one of the hard things about studying the brain compared to, as you said, compared to like a model, is that you can't just, like with a model, you just pass the same input and it just outputs the same thing. You don't have to like, that's kind of the advantage of a model. It's much more reliable and reproducible. In the brain, we don't have that, right? There's this inherent stochasticity. And so what we do is we actually account for, so not me particularly, but the neuroscientists do the hard work that collect the brain data. They collect multiple trials of that condition. And that's how you get a statistical estimate of the inherent variability of the neuron. So that on a trial by trial, how internally consistent is a neuron with itself, basically. And that sort of sets like a one baseline where you correct by it, basically. You kind of like divide it out. So you know, okay, look, like whatever variability I'm going to expect is going to be with respect to, you know, at least the neural internal consistency. But at a high level, like, the thing that also additionally matters a bit more is there's also evolutionary variability between brains. So in other words, like if I look at the same brain area And even if I did like the best possible job of like putting the electrodes in the exact same place and likewise in the other animal's brain, I cannot guarantee that they're going to be exactly the same. Even if the brains were completely deterministic, in the best case that the internal consistency of the neurons was 1.0, right? I still can't guarantee that they're not going to have some variability, because at the end of the day, look, these brains were evolved. There's going to be natural intersubject variability. And so actually with my co-authors, Janelle Feather, Meenakshi Khosla, and Ratsan Murthy, we just put out something called a NeuroAI Turing test, basically, which is that basically the key principle is that given some metric that does this correction for the internal consistency, so you're accounting for the fact that neurons are variables, the main kind of baseline ceiling that you want to actually match is that the model should be as good as brains are to each other. So in other words, brains are going to have this variability, either in terms of their outputs, the behaviors that they're going to take, the strategies they're going to take, but also in their internal computations too. And we want to account for that variability, measure that variability, and we say the models should be at least as good as the brains are to each other. And so that's one of the key ways that we account for both the inherent stochasticity of the brain, but also the really like the core like functional differences in the brain that can come up. So we know that it's not just due to, we got the model wrong, but it's that also the brains were reasonably different up to some ceiling of variability.
Right. Can you talk about your NeuroAgents lab and some of your updated works in building these embodied agents? And you mentioned that you're working with mouse models and monkeys and also human, and also the role of virtual reality, because I believe that you in simulation, you're training, you're using virtual reality, right? Would love to.
Yeah. So actually, I'll start with the virtual reality just to begin with, because I think that grounds a lot of the discussion. For some time, I remember grappling with whether I should just kind of go try to build real like hardware-based robots, or try to develop these things in sim. And over time, I've kind of just settled on simulation for a number of reasons. One is that in science, especially in this kind of field where like everything, so much is unknown, and like what I call like, I guess the science of intelligence. So this kind of intersection of neuroscience and AI and cognitive science to like try to understand how intelligence arises both biologically and engineer it as well. That like the main thing to look for here is to fail fast. And moreover, that the type of body that animals have vastly different bodies, right? There's animals on 4 legs with different, ratios of their limbs to their body mass, right? Or they're bipedal like us. And so, there's just no way you could like build that. That's going to enforce a lot of constraints, right? At the end of the day, the brain is taking inputs, and what is an agent, right? It takes inputs and produces actions, outputs, right? And those outputs are going to be funneled through a body. And so the body's going to form a huge constraint. And right now, the current hardware in robotics is just not good enough, really. And it's very brittle too, right? Like we're not even good algorithmic cysts who come up with good algorithms, that we don't break these robots every time we do something. And not only that, even if we didn't break them, the hardware itself is actually quite limiting. And I think that ends up putting too much of a constraint on the questions. And lastly, in the real world, it's like, you have the wall clock time of the world. So you can't speed that up at all, and you can't fail quickly. In other words, at like maybe like the best case scenario could be that you like are a little bit faster than evolution, but that's too long. So it's often better to like put these in simulation and use biomechanically realistic bodies that you can develop much more easily in simulation and control, right? And so the key to science is, can you control a bunch of variables? And you can in simulation. You really cannot do that in the real world. At some point, though, the real test is ultimately in the real world. So I do believe that we should definitely do Sim2 Real and all of that. But when it comes to just figuring out the base principles here, I think simulation is the way to go. And an added kind of cherry on top is that actually a lot of neuroscience experiments are also doing things in virtual reality too. So, people right now, for example, people who want to study navigation, they won't actually go and build like a box that's very complicated with lots of different towers for a mouse to go in. I mean, some people might do that, but in general, it's actually much easier to like put the mouse on a on a running wheel and actually project a VR screen and then program the different obstacles and things there. And this is really nice because it not only gives experimentalists control, but when we go and test these models against brain data, we can actually literally put it in as close to the same scenario as possible because that was collected in VR too. So we can actually literally port that over. So there's kind of less of this gap of like experiment to model testing that used to be the case when people would mostly do their experiments in the real world. So yeah, I think VR is really important. The other aspect of it is that, ultimately when we're building these agents, a lot of the like tests in VR is first, are we even getting the behavior right? Like before we even go and like compare to the brain, it's like, is it actually doing the reliable behavior that we know the animal does? So one of the big challenges, for example, with reinforcement learning, especially end-to-end reinforcement learning where you're training from scratch, is that it can often not be very reliable. So you train it for a policy and then either it takes a lot of time, but even in the best case where it does converge, with different seeds, different environments, it might just do very different and unpredictable things. But animals, on the other hand, can produce very reliable stereotype behaviors. So animals, for example, will learn to give up after a while and not spend their energy resources. So they have intrinsic drives to like learn to give up quite reliably within a certain period of time. You don't really see this in RL agents right now. And so, for example, RL agents, one of the things is like trying to figure out what those intrinsic drives are. Because a lot of RL, like unlike, in games like Go and chess, where you have a well-defined external reward, the real world environment doesn't have that. So they rely on intrinsic drives that are handed down from evolution to be able to do this well. And we're just trying to first like reverse engineer that and get back reliable behaviors before doing other things, basically. And like, for example, before comparing then the internals of the models of these agents to whole brain data, we just want to see, can we even get like reliable behavior as just like step zero? And that's already a challenge. It's very interesting to us.
Right. I don't know, how does the Sim2 real world transfer happen? What's the challenges over there? Because Sim, obviously it's really cool to kind of tinker around and train these models. What's the transfer from challenges in Sim2 real world? And as you build these these reverse engineer these animals to build these autonomous agents, what's the wildest animal behavior that you've kind of modeled?
That's a great question. So, so like in the first part of this, it's the Sim2 Real, like the major challenges are, not only the standard kind of robotics ones, which is like, the lighting changes, the shade changes, shadows, for example, are really important in the real world that we don't always really think about in Sim. The way the sun is up at a certain angle could affect, just the vision system alone. But the other aspect of it is just like more specific to like what we do is that, the bodies that the biomechanical realistic bodies are quite high degree freedom, like, 102 degrees of freedom, right? Like I think a spot robot is in the tens of degrees of freedom at best. Which is already high for a robot, right? But in Sim, it's a lot higher. And so there's already a kind of gap between like, if I want to go put it on a quadruped, but like I trained it on like a more of a mouse body, there might be that gap. So first, in some sense, you'd want to then take that algorithm that you kind of match to the brain, but also try it in a simmed quadruped and then hope that it can transfer, barring the first issue of the terrain and lighting and things like that being different. But so there's this kind of body transfer gap. And then the other aspect of it is like energy preservation, right? So, real world bodies like have battery lives and those things get drained really easily. So you have to be careful about, this is one of the reasons why we want to like sort out these kinds of intrinsic drives that prevent perseverating on unlearnable things, which is a current like algorithmic challenge, is that, like if it does do that in the real world, it's over, right? It drains itself of its resources and that's it. So it's just like, actual death scenarios and like injuring itself that just doesn't really often happen in Sim unless you just, end the trial, right? But then you just get to restart again. Whereas in the real world, it's like you broke your thing and now you have to buy a new one or fix it, right? So it's really that kind of iteration is a lot slower and can be much more catastrophic. You were asking though, you had a second question though. Related to that.
What are the wildest animal behaviors that you've modeled?
Yeah. So, so far actually we're starting with things we that are, reasonably controllable, but naturalistic nonetheless. Like this reliable kind of like energy preservation. One of the more wilder ones right now that we're getting into, is, actually, I can tell you that, I related to kind of physical embodied intelligence actually was that, trying to better understand internally, like how humans and animals build mental models of the world to be able to make physical inferences, short-term physical inferences. So how do we build like an embodied understanding of how physical objects behave just so that we can, draw inferences about the world, but also act and operate and plan in it. And one really cool thing, which was by a collaborator of mine, so this is when I was at MIT, Rishi Rajalingam, in Mehrdad Jazayeri's group, he like trained monkeys to play this game of mental pong. So what this is that basically they're operating a joystick, and it's just like the normal game of pong. But what happens is that right before the ball hits the paddle, which is why they have to modulate the joystick to intercept the ball and get reward, the ball kind of disappears behind the screen. And so one really cool thing was that in the frontal cortices of the monkey, more precisely dorsomedial frontal cortex, but they found that actually the monkeys were simulating the ball's position and velocity in its head to be able to do this calculation and do this well. So they found signatures of that in the actual brain, playing this mental pong tack, which it's not a naturalistic behavior. It's still weird you're getting a monkey to play a video game, but it's like, to me, just so cool that like you can even do that, and that you get this reliable like mental simulation that's going on, that we then go and build a combination of video foundation models and future prediction to build these kinds of latent future prediction that we found was important, because actually many of the models failed to match this data. It was very constraining and very interesting.
Aran, who are the other guys who are taking this approach? Because there's Professor Daniela Rus and Ramin Asani, who are working on the startup called Liquid AI with something called as Liquid Foundation Models, where they are reverse engineering a C. elegans worm, and that's like 302 odd neurons. So who are the other guys? I mean, researchers and companies in the space, who are taking this approach of building, reverse engineering an animal to build autonomous agents?
Yeah, so I think it's a quite small space right now at the moment. So it's an interesting time where, right now a lot of the focus in industry is what industry does best, right? Which is to collect lots of data and really do that really well, collect high quality, good data and just like scale it up. And like maybe less of the focus is on developing new algorithms. So I'm sure there are some of that, right? So for example, like I mentioned, for these agents, we want the modules to update over time. That's kind of like a simplified version of what I just described is actually, test time reasoning. So, right, it's not updating the weights or anything. It's just doing the reasoning. But it's that kind of thing where like we need new paradigms like this, where you're actually doing the update, the lifelong learning in real time with the new scenarios you're encountering. Now, what we ideally want is that the weights update too, right? And you can actually and the connections between the modules can dynamically rearrange. That's something the brain does really well that we still haven't figured out good algorithmic solutions to. But it's again in this flavor where like people in industry are starting to pay attention to the fact that like just doing basic things like test time reasoning, it's not like some major algorithmic advance, right? It's just RL applied to these kind of question answer pairs. But just the idea of doing it rather than just pre-training alone, going beyond pre-training has already yielded like practical returns on investment. And so I think right now this kind of going further with that and like, rooting it in the brain as well, where we are getting this data, is largely an academic one than a company-based one, because it's hard to take bets as a company where you have to show like a product market fit value in 2 to 5 years, when these are ideas that can take potentially longer than that, hopefully not too much longer, but you can't guarantee it. And so it's something right now, I think in academia, like the key is not to work on the existing thing. That's something industry can do much better. But it's to collaborate with industry, especially, where they can put in the resources, but to really focus on the next big thing. And I think this, because this is more like the next thing, it's we don't yet see it right now as dominating the conversation or in industry. But it certainly, of course, has to be that's what AGI is, right? Is interacting with the world. So it's an inevitable thing that we're wanting to build good agents. But how we get there, I think, is going to require a collaboration between industry and academia.
Right. Yeah. So I mean, surely, I mean, what's happening with the statistical data models, data in, data out, they are not the right approach, because that's not how we humans, think and function, So, assuming this NeuroAI approach should be the right approach, you said, like, I mean, that it could take time. I mean, do you have an intuit, like what's the timeline? Do you think that to kind of build this possibly reverse engineer, maybe like an animal, start from there and scale it? Because I guess maybe if you're able to do that, like reverse engineer an animal and build a model, and obviously I'm sure we should be able to scale, and I'm sure that would solve so many problems. You won't need the data, you won't need the energy, and so on and so forth. What's the intuit?
Liable behavior. Yeah, that's a great question. So, I think to like settle on a timeline, one has to also settle on the goal, right? So at least my own goal isn't to model every biological detail. You could do that, right? And so like folks who work on the Connectome project, they really, really care about doing that to like biophysical detail. I think that sort of thing. I mean, look, you already, like, forgetting just the connectome of the fly itself, I think took at least 20 to 25 years, if I am remembering correctly. Now, technology is improving this. You do it once, maybe it'll be faster the next time around. But I wouldn't really put it. I mean, but again, that's just the connections. It's not how they update. So I think if you're going to go with full biophysical detail, which I'm not saying you should, but if you wanted to do that, that was your goal. I mean, easily a century would be already that. But I think to get to like practical, like AGI that like you and I, agents that are just capable of like doing tasks, for 24 hours autonomously. Let's just say that's the goal. I don't think you need to really model the brain biophysically at all. I think you just need to like think common sense, like what are the behaviors that we do well? Let's go and just like build that in and be inspired by the brain, but not so much try to copy every detail. In fact, to understand the brain really does require, summarizing it and abstracting over it and forgetting about the details that maybe evolution, put in, but it wasn't necessary completely for intelligence. So I think for an agent that like can run, if that goal is, say, I want an agent, not even embodied, okay, just like a digital agent that can run for 24 hours, something like a couple years, I think it's a fair timeline. I mean, it could, of course, there could be roadblocks that make this longer, but I think at least 2 to 3 years is not crazy. I wouldn't necessarily call that AGI, right? But I would just say that's useful and a capable autonomous agent that already would go beyond its pre-training data somewhat to be able to be capable.
Right. Aran, the approach that you're taking, do you think it would be a better path to go towards maybe conscious machines? Because, at this point in time, I don't think anybody's gotten even an inkling of what consciousness is. But when you're talking about these embodied agents, I mean, with these LLMs, I'm sure they'll just be zombies, because they don't have the sense of who you are. You think this reverse engineering, possibly animals, maybe because we could lead to maybe sentient autonomous agents?
That's the hope. So right in principle, I don't see any reason why things like consciousness, whether we want to agree on a definition or not, aren't physical manifestations or physical processes. In which case, I don't see it. Unless there's some new law of physics that I'm not aware of. It'll be, you can put it into a computer. And in fact, I remember about like 10 years ago, I was very curious about physical manifestations of computation. So I wrote an article about like a general negative answer to hypercomputation. So there's a belief that some people have that consciousness itself is some like non-Turing computable quantity, and therefore you can never put an algorithm in. That would be the barrier. But I show in that article that that you'd actually have to like go within the current, like, you know, what's known about physics. There's nothing that would prevent these things from being constructible. And so you'd really need to go and posit some new law of physics that is yet unobserved to claim that it's not possible. And so folks like Stuart Hameroff and others, of course, are right. And so that's like, some notion of quantum gravity that doesn't have any experimental grounds in it. But just to say, like, if you really wanted to, in principle, claim that, just as they're doing, you really need to move beyond the current what we know about the physical world. So, and that's what they're doing. But I sort of think of it as like that's a much larger step to take. It's much more of like an Occam's razor principle of like, well, look, like, you know, the physical world is what we know. We know how to get there. And so I see no reason really that these fundamentally why brains aren't or things like consciousness couldn't be manifested in a machine. The core thing though is that, you know, this is partly why I think actually doing NeuroAI or like comparing to brains is actually essential when it comes to something like consciousness, is that even if we don't agree on a definition, we all agree that it's in a brain. It's in a biological brain. So if we ever wanted to have a scientific consensus on that notion, which we don't have at the moment, we have to settle it in the brain. So we have to have some comparison of the machines to brain data, or some observable that's in the brain. Assuming we all also that's our goal, right? And so I think that it could totally be fair that we build intelligent agents that in the future might later on be validated as conscious. So in other words, I think the engineering of these agents will come first. Whether or not they're conscious and whether or not we agree on it will have to come with a scientific understanding of the brain, because inevitably that's where, I mean, it doesn't matter what our definition is. We all agree that it's in the brain. So we have to understand that. And that's just going to take a much longer time than building intelligent, capable agents. And, you know, just because they're doing intelligent behavior, of course, doesn't necessarily mean that they're conscious, right? So, for example, right now, LLMs are more capable than a C. elegans or like any living organism, you know, other than us, right? At generating text. But I don't think that means they're conscious, right? Just because they're capable of doing that. In fact, my own wager is that they're not, for my own personal unscientific definition of that quantity. But the core thing is that, you know, an animal, for example, has a desire to survive and a will to live. So it could be that, let's just say hypothetically, that's going to be part of the scientific definition of consciousness. Then looking to the brain and how that's mechanized, what are the mechanisms of that, will be necessary to identify, so that we can then go and check those in machines. So that's what I mean. It could just take much longer than building it.
Right. Aran, supposing in a hypothetical future, you're supposed to kind of, you are able to kind of, reverse engineer an animal and build a sentient machine. And I mean, what would be the question that you would be asking a sentient machine, and why?
That's actually something a thought experiment I do to myself for some time now. That's a great question. My desire with these machines is more to like understand the nature of reality. And maybe that's just because I'm naturally, biased to be a scientist. And so that's obviously the scientist's definition of what they would do with such a thing. But one of the reasons for this is that, I don't know, I guess I want to sort of peel back the fabric of reality better. And I think there's no better way to do that than to bootstrap intelligence. And in particular, one of the great capabilities the machines have always had, compared to us, is the ability to process and experience large amounts of data and find some kind of patterns. Now, machines aren't 100% better at it than us. Like, I think right now, like, human scientists are better at things than AI scientists, but I think that'll change. And that's not always going to be that way. And I think once we have these more capable AI scientist agents, that would be the key thing, is like to collaborate together to like better figure out why we're here, if that's even the right question, what's the nature of reality, those sorts of things. Now, I don't think that they're going to be able to run all experiments instantaneously, right? We're all still going to be somewhat constrained by the physical world. But as we get better at understanding certain physical processes, we can simulate them. So kind of related to our earlier Sim2 Real discussion, you can do real back to sim. So in other words, once you understand something, you have a good computational model of it, you can go and put it in a computer and simulate it even faster than running those experiments. And that's one of the motivations actually for NeuroAI is that, once you have an in silico model of a brain area that's pretty faithful, you can then go run like thousands and hundreds of thousands of causal perturbations and interventions to learn about things far more quickly than you could in the real biological brain. So I think it's going to be incremental. We're always going to be somewhat constrained by, say, the speed of light and like other physical quantities. But as we start to better understand things, we'll then put them in simulation and run them faster and then generate the next set of predictions and so forth. And so that kind of collaboration, I think, to better understand reality would be the sort of things I would want to ask and query such more capable agents, even now too,
Right. Interesting. So the nature of reality, I just want to kind of, push that a little further. I'm invested in virtual reality. We're building these virtual world and metaverses, and every year I see this rapid progress. These 3D engines. They're able to build these photorealistic world, and I'm sure in the next possibly decade or beyond, possibly maybe structurally and functionally, if you're able to kind of map a human brain, we'll be able to create these maybe understand a human brain better and possibly build these haptic feedback or possibly these brain computer interfaces through which possibly we would be able to emulate maybe all of 5 senses, sight and sound. Obviously we do it very, very well, at this point in time. When you're in virtual reality, it can be like really, really cool. With the audio, we do these ambisonic spatial sound, which is like as real as, how we kind of, hear sound, and then it's just touch, smell and taste, we kind of pushing that, and I'm sure as technology kind of accelerates, we should be able to kind of, mimic all of 5 senses, so there's this conversation, there's this people such as Donald Hoffman, and many others who kind of believe or talk about that, this thing, Donald Hoffman, Nick Bostrom, who says that the reality itself is simulated, and Donald Hoffman has this theory that, space and time it doesn't exist, basically like a virtual reality headset. You spoke about the nature of reality. What's your thought on this this other bunch of people like in Donald Hoffman, Nick Bostrom, Elon Musk, Joshua Bach, and many others who think that possibly that whole reality is nothing but a virtual construct?
I think I often worry that this might be us like just taking the latest technology and kind of grafting it onto reality, right? Like the computer in this case, right? And not to discount it, I just sort of, I'm not certain enough, in other words, I don't know enough about the nature of reality to speculate. I just want to know what the answer is regardless. But I think, one thing that's curious about computation that's different than maybe all the other, people can say like, okay, would a watchmaker think that the moon is made out of gears, or that the moon is made out of cheese if they're a cheesemaker, right? That sort of thing. One of the things that like differentiates a computation, I think, from any kind of invention that came before it is that actually it's a quite fundamental notion. In other words, that there's a notion of kind of like Turing universality, that there is like equivalent ways to do the same thing. That it doesn't matter actually the physical implementation of how do you do it, but it's that there's a power, a level of ability to do a computation. And I think that universality always, that sort of thing always is basically the fundamental building block of any kind of important, like more universal principle. And so I think going forward as we enter a new age of science, I think things like information and computation will play larger and larger roles in how we understand the world, and they probably should. So in other words, like I think maybe we didn't account for it too much in the before the 20th century, really. There were hints of it, of course, like the Greeks and the Persians, they had algorithms, right, and that sort of thing, but they didn't understand that this was part of a larger class of like equivalent ways of doing similarly complex things, right, of a process. But once the notion of a computational process was formalized and built and really executed, that's when we started to make a lot more progress. And I think that these notions of computation and information are fundamental, just as any other physical law is, and that they're going to start to play a bigger role. And we're already just seeing like inklings of this with like AI, kind of interfacing with everything's like AI plus biology or AI plus business, AI plus X, right? And I think that's just really actually a special case of this larger principle of really integrating computation and information more deeply with the natural sciences. And I think going forward, it's just going to continue to be an inevitable thing. And we'll see where it leads, because they're quite fundamental notions, but just carrying things out. And when something is a fundamental notion and you're taking chance to really exploit it and understand it, you're very positioned to like figure out something new and fundamental about the nature of reality.
Right. As an educator, what's that one piece of advice that you would like to give young researchers who want to kind of tinker around with what you're doing? This interdisciplinary approach of neuroscience, AI, and robotics.
Yeah. So my major piece of advice is really don't follow the latest trends, but really follow your interests and try to listen to your inner voice of what really naturally excites you. And I know that maybe sounds a little cliche, but actually in my case, it was a piece of advice I got when I was in college. I was struggling to figure out what I wanted to do. And I was actually, I have a theoretical background. And it was trained in math and like theoretical computer science and that sort of thing. And actually, recently that became useful for some AI safety work of like, in theory, theory is really great about, understanding or like reasoning about things that haven't yet been built yet. So I think for AI safety, theory is like really useful. So we just showing, that there are fundamental barriers to things like alignment, and maybe that's not the approach to get to safety. And I wouldn't have anticipated that if I didn't have the background. In my day to day, it's largely empirical, because it's faster to just run something that exists than to like prove a theorem about it or like have a lot of assumptions, right? But when it comes to things that don't exist, I think theory can be useful. And one piece of advice that I got when I was, trying to figure out what I wanted to do is I always knew I liked the brain. I was just always drawn to like intelligence, that sort of thing. Keep in mind, this would have been like 10 years ago or so, 12 years ago, where like deep networks actually still weren't the rage, right? And people had debates about whether there was even like symbols versus like distributed representations in the brain. I mean, now that's pretty settled, like the way she used neural networks. But back then it was really unclear. And that just was so cool. So, and I was always like interested in kind of like questions of like the nature of self and reality. And it seemed kind of clear that we wanted to understand intelligence to make great strides, right? Just as like physics and chemistry were, the study of inanimate things and led us to great advances in material science and engineering and building devices. I think the science of intelligence is the next thing that would yield to even exponentially greater change. Imagine if you could imbue that into technology today, and I really do. I mean, it's hard to imagine where that can go, right? And so I just kind of listened to that voice that like, you're interested in intelligence. I wasn't particularly drawn to computer science purely. Like, I wasn't that interested in like only being good at coding or pushing on one benchmark or something like that. I really did care about like trying to use I knew that computation is fundamental, but I was always interested in using computation to kind of better understand how our intelligence works in a mechanistic way, like really trying to pin that down. What does it mean and all that? And so that's kind of what led me to go from math to, math I think was great for like setting your logical reasoning. Computer science is great for, really putting those things into practice, implementing things and really testing them out and dealing with the real world bugs. And then ultimately doing a PhD in neuroscience after my master's in computer science and like being faithful to that inner voice of saying, if I want to understand the brain, I got to go see like the people who actually like deal with it on a real day-to-day basis. What do they have to say? And so that trajectory kind of, as a result, looks interdisciplinary, not because I wanted it to, but because at each point along the way, I listened to that voice, and it ended up being necessary to pick up the tools from that and really learn it. And I think that's, I know right now, large language models are the trend, and everyone wants to use them in their work, and I think that's great, and I think they're going to accelerate a lot, especially for students today, right? I actually encourage my students to use it when they can, but also be careful and to verify, when they encounter it. And so not as a substitute for thinking, but as an aid. And I think that's great. But I think that you should look towards the future. What is the future? What do you think the future needs? And if there's some skill set that you feel that speaks to you about what the future needs, then listen to that voice and follow it rather than chase the current trends.
Right. Completely. Aran, my last question to you. What's your moonshot? What comes next for NeuroAgents Lab? And will you be able to paint a picture for us? What do you think happens in the next 10 years, with this convergence of tech stack, with these LLMs and these possibly neuro-inspired AI, when it actually comes together and we have these machines, this huge goal that we're going after, artificial general intelligence, whatever approach kind of, bring us towards that. How do you think it's going to impact our society? Because at least from my perspective, I see that there's earlier was an arms race, and today it's this AI race for dominance, which is going on. And I believe that the only way towards a better future is collaborative, not conflict. So it would be great if you can leave your thoughts with the audience.
I totally agree with that last statement about that the future should be collaborative, not competitive. So I've always, one thing I benefited from when I was a student was that the internet was a thing, and I could just go look up whatever I needed to learn and teach myself things. And that was huge. And now it's way easier. Now you have LLMs where you can just query things and get back, some reasonable response. It may not always be accurate, but something that kind of can guide your understanding and is personalized to you. And I think in the future, in very near future too, that's just going to continue to be the case. And extrapolating to the future, I do feel that right now things might seem competitive, but I think actually naturally as information becomes more free and also accessible, that it would actually just naturally converge to collaboration. And especially as we start to build, what's the moonshot? The moonshot is building these generally capable autonomous agents, not long horizon, not long-term planning, but literally lifelong learning agents. And that to me is the moonshot. You're basically, ultimately not only better understanding ourselves by doing this, not by copying the brain, but just understanding the principles. Just like in an airplane, it doesn't copy the feathers of a bird, but it captures the Bernoulli principle. Figuring out those Bernoulli principles for intelligence, for the science of intelligence, is going to be critical for building, an important aspect of these autonomous lifelong agents. And so that's the moonshot. And I think our society would change in a way that's quite unimaginable. But I think one aspect of it is that if you're building a new species, quite naturally, us as a species would be more collaborative and united to kind of, make sure, one, that's safe and safely deployed, but also two, the access to information is just going to get more and more. That right now these kind of, disagreements or privatizations or putting walls on things is just going to seem petty and kind of childish and honestly, like the myth of Sisyphus, always they try to do it and then the ball rolls back down the hill and they'll try, but it's inevitable that it will just continue to be free. And that's at least my hope, is that leads to much greater prosperity for humanity as a whole.
Thank you, Aran. Really appreciate you taking time and being part of the podcast. I wish you and your team go towards that world where we build machines that is not just data hungry and power hungry, but are actually doing something what we do, mimic biology. Because I think, if we someday are able to do that, it would be wonderful. But it's also obviously, what would, because even animals and even humans, we have our own biases and issues, so I worry about that. But yes, I'm sure, there would be a way to kind of, make these agents, autonomous agents, which is more aligned to humanity. And I hope that what you wish for, comes true. And thank you once again for taking time and being part of the podcast. To my listeners, if you like what you see in here, then please press the subscribe button. And until next time, thank you. Thank you so much. Thank you.
Thank you for having me.